Thank you, Forrest. Good afternoon, everyone. When I told my 9-year-old daughter this morning at the breakfast table that I would present our latest chip here at the conference, she replied quickly, "Yes, it's very tasty and crunchy in your mouth." Well, not quite this one, but the PNX 85500 is a single LCD chip TV that contains all the features required for a great TV experience, so you can enjoy these chips in front of your couch, or on the couch. Let me start with a quick outline of what I'm going to talk about. After a brief introduction, I will show you how much more TV system we have packed onto a single chip, and how few other components are required for a complete TV system. I will explain the major challenges we faced and how we addressed them. And before I conclude, I will present a couple of video functions that demonstrate the valuable features of this TV system. First, let me explain two terms. The PNX 85500 refers to the world's first digital TV SoC at 45 nanometer, in 45 nanometer technology. That SoC is the heart of the TV 550 system, which also includes the associated TV software and other components making up a complete TV reference design. Moving to 45 nanometers allowed us to achieve extremely high levels of integration. The SoC contains channel decoders, source decoders, all kinds of networking interfaces, and enhanced picture quality improvement algorithms, allowing to directly drive 120 Hz panels. The TV 550 only requires a dual 16-bit DDR, providing the industry's lowest bill of material and allowing TV manufacturers to limit the number of different platforms they need for different regions. It enables the development of a global chassis. But let me take a quick step back. About 15 years ago, Philips Semiconductors brought the first one-chip TV to the market, which did support analog TV reception. Tomorrow's TVs need to do a whole lot more. They probably won't make you coffee yet, but they require a much more complex system, which we have integrated in a chip. This block diagram depicts a typical digital TV system based on last year's product. On the input side, you have tuner, demodulators, channel decoders, or analog and digital inputs. All inputs are hooked to a front-end TV SoC, like a PNX 8543, which supports 1080p video resolution at 60 Hz. But if you want to drive 120 Hz panels, you do need an additional frame rate converter, like the PNX 5120, with its own memory. You have a wide range of interconnectivity, but need an external MAC. The TV products shown here are based on 90 nanometer technology. Skipping 65 and going directly to 45 nanometers allowed us to achieve unprecedented levels of integration. Everything shown in the green box here has been integrated in the PNX 85500. Actually, the 128 megabyte DDR memory up here, which is used for the frame rate conversion, is not integrated, but it's now obsolete. So you can already see that there are very few components around that single SoC to build an actual TV set. You can achieve the highest level of integration for a DVB television. It's amazing how few components are needed to actually build a complete set. You can build that TV with basically just a silicon tuner, an HDMI switch on the input side, and flash memories, flash and DDR memories, an Ethernet PHY, and an audio amplifier. Everything else connects seamlessly to the 85500. For ATSC and ISDBT, the channel modulator is not yet integrated, but except for this additional component, the TV platform can be identical, which allows TV makers to use the TV 550 as a global platform for a worldwide solution. So enough of that marketing talk now, and let's look closer at the SoC. Here you can see a block diagram of the complete SoC. I won't go into details of each module, but we'll start with an overview showing which modules are responsible for which function groups. Let me start with generic control modules, including the OS and interconnect. See them highlighted here. A second group of IPs is related to transport stream or digital broadcast and transport stream processing. A fairly small number of IPs is needed for audio processing. And as you may expect in a TV, the largest number of IPs is related to video and graphics processing. Now I want to illustrate video data flow very briefly to indicate the raw memory bandwidth for a simple use case. That use case is H.264 1080i decoding with a graphics GUI on top of it. And what you should realize is that for 120 Hertz output, if you output 120 Hertz at 1080p, you have a pixel rate of about 250 megapixels per second. For one single 10-bit YOV42 frame, that translates into 660 megabytes per second for a single frame. So in that use case, the decoder takes the compressed data out of memory and stores the decoded frames at 30 frames per second and interlaced back in memory, generating a modest bandwidth of about 350 megabytes. Then we have the video scaler that converts the images into 4:2. It de-interlaces the picture, applies noise reduction and other processing. And as it creates output at a progressive rate of 60 Hertz, it actually generates about 1 gigabyte of memory raw memory bandwidth. For the 120 Hertz output, the frame rate converter has to take 2 input frames for every output frame, which adds up to a raw bandwidth of about 2 gigabytes per second. Then I mentioned we have a graphics GUI. For that, the processing is done in 32-bit RGB, but at a lower refresh rate and actually just 720p resolution. So that only produces about 200 megabytes. But on the output side, at the video composition pipe, we have to output each layer at a 120 Hertz rate, which adds another 1.5 gigabyte per second. So just for the raw video data, we would require a bandwidth of about 4 gigabytes per second. Keeping this bandwidth in mind, I will now focus on the major challenges that we had in this design. Let me start with the organization. Many of you have probably had similar experiences. The combination of cost pressure on this side of the ocean and significant increase of complexity has one impact that does not simplify or not increase efficiency. The development has to be run as a highly multi-site project. In NXP, this picture only shows 8 sites. I have to admit that I actually forgot one of our teams in Belfast, a small but crucial team there. So we actually had 9 sites involved in the development of this project. The SoC consists of about 100 IPs from small adapters to large and powerful trimedia VLIW processors. And to give an impression of the size, all the IPs in the design add up to about 300 million transistors. And they use about 100 billion vias on the layout. But complexity not only stems from the number of IPs, it's largely to the extent of the very heterogeneous architecture. There are a lot of different modules that were not specifically designed for the SoC, but they were pulled out of different solutions and now have to work together in a single SoC. There are hardware modules for established functions like analog video and analog audio inputs. There are high-performance modules for functions like video decode, video scaling, video composition. Then there are RISC CPUs, in our cases MIPSs, to run control processing, the operating system, and flash operations, as mentioned just before lunch. We use a Termedia VLIW processor as flexible DSP for audio decoders, internet video codecs, and programmable video algorithms. And then we have a high-performance DSP with hardware acceleration for the frame rate conversion at 120 Hz, also called motion-accurate picture processing. So when we started the definition of the PNX 85500, we looked at all the functions that had to be integrated in a single SoC and concluded that we would require a 64-bit DDR interface. But the requirement for marketing was different. They wanted us to make the system work with just a dual 16-bit DDR2 1066 memory with a gross bandwidth of 4.2 gigabytes. The actual bandwidth, of course, that you get on DDR2 highly depends on the efficiency of the transactions. And with the mix of the IPs that we have in that SoC, we get an average efficiency of about 71%. So the maximum bandwidth that we actually get out of that memory is closer to 3 gigabytes per second. Another huge challenge was memory latency. Memory traffic from the processors, you see the 4 critical ones in here, very much depends on latency. The stalls have a big impact, iCache and Dcache stalls, on their performance, especially on a small MIPS, one of them which just has a 16-byte cache line size. On the other hand, there are several high bandwidth video IPs that produce very predictable traffic, but need to meet strict real-time requirements. Having a video frame drop or duplicate, even a slight picture quality degradation due to internal overflows or underflows is not acceptable to any TV manufacturers. So in order to meet those challenges, we had to come up with solutions at different levels. The processors have low latency ports on the memory controller, and we had to identify different arbitration and scheduling schemes for the different use cases. The bandwidth-hungry video IPs, as well as the VLIW processors, use hardware prefetching to make data available before it's actually being used and to reduce bandwidth peaks. To reduce the effective bandwidth, we implemented additional caches and local buffers at several hotspots of the SoC infrastructure. Let me give you one example here, and that's the frame rate conversion subsystem. In the PNX 5120, the previous product, we had implemented the frame rate conversion by fully programmable on 3 Termedia DSPs. That approach worked very well in a standalone SoC, but it was not suitable for multiple reasons. But its main disadvantage was the high dependency on memory latency. So we came up with a new approach, combining a powerful 8-slot VLIW Termedia with a dedicated motion estimation and compensation coprocessor. All pixel processing is performed in that coprocessor, which actually contains 128 kilobytes of 2-dimensional cache. This reduces area and makes the subsystem very tolerant to long latencies. And last but not least, the SoC infrastructure also supports streaming, hardware streaming of video data from one IP directly to another, avoiding the need of all video buffers to be written to and read from memory. So getting high memory bandwidth under control is one big challenge. Another one, however, is verification. How do you make sure that all the IPs actually work together when the silicon is available? Verification has to be done at different abstraction levels. The dimensioning and verification of the SoC infrastructure is initially only done on an Excel spreadsheet, but from a very early point in the development on, we deploy system performance verification of the SoC infrastructure, including all critical IPs. Another crucial step that makes a tremendous difference is the usage of a SoC emulator. It typically achieves a speed of about 1/1000th of the actual hardware only. So for example, 500 kilohertz rather than the 500 megahertz for a Termedia processor. This may be slow compared with real silicon, but it's still very much faster than simulation speeds on compute platforms. It's also important that we use the emulators for the development of the actual system software. So before the PNX 8500 tape out, we had all major use cases running on the emulator with the actual software. That guarantees that once the silicon arrives, software is ready, the picture quality has been verified, and all critical performance settings have already been tuned. All this together ensured a very fast silicon bring-up when the silicon arrived. So talking about silicon, here's a photo and a layout image of the PNX 8500. It's produced in TSMC's 45 nanometer low power process technology and packaged as a flip chip on a 27 millimeter BGA package. The interesting thing about flip chip is that if you're curious about die size, you no longer have to open the package. You can just take a ruler and measure the sides of the die that are exposed. So if you take a ruler and look at this one, you'll measure about 8 millimeters on each edge, and you can easily do the math of how big that would be. Low power to increase battery life is not really a concern in a TV, but with these ultra-slim chassis of side-lit LCD TVs, there is very, very little room for heat sinks. Therefore, it helps that the PNX 8500 requires less than 7 watt, even in the most demanding use case, and does not require active cooling. In this last section, I want to highlight a few features offered by the PNX 8500. I mentioned earlier the complexity caused by the number of different IPs in the SoC, and you may imagine that some of the IPs themselves are fairly complex, like a VLIW processor. But I want to give 2 examples of video IPs, as some of you may not realize what complexity hides within them. Here's a block diagram of the video scaler. It is made of a large number of sub-IPs, not just scalars. You can see pixel fetch units on the left, processing blocks in the center, and write interfaces on the right side. I just want to point out a few examples of these processing steps in there. One, of course, is a scalar. There are horizontal and vertical scalars in here, multiple instances of that, actually. In order to convert interlaced input to progressive, we have the deinterlacer sitting there. Temporal noise in the video's input signal is reduced by that TNR block. MPEG artifacts, like blocking, are removed by that VCAR module. And a different kind of block, there's the P-core block, producing projection data, which is used for the film detector to figure out if an input source is film or video. Even more complex than that video scalar is the video composition pipe, which outputs the data at 120 hertz. Let me also point out a few functions. Some of them are fairly well known and common, but some of them are a bit different. The PCTI improves color transitions, which often get blurred during the transmission chain. And there's a module that improves the overall sharpness of the image. If you ever wondered why the blue sky on some TVs might look better than on others, this module will specifically detect blue color in the sky and improve it. And not just the blue sky, also skin tones of people are detected and improved by this one. There's a 2-dimensional dimming backlight, of which I'll talk about more in a couple of slides. So this slide explains why the frame rate conversion is such an important feature. Original movie material, even shot, or even on a Blu-ray disc, it's usually shot at 24 frames per second. In order to get it to 50 or 60 hertz display rate, which is used on older TVs, each frame can simply be repeated 2 or 3 times, introducing the infamous movie judder. But if you've had a look at recent Fry's ads, you probably found that 120 hertz LCD TVs are now becoming mainstream. So in order to eliminate the movie judder and also reduce motion blur for 120 Hz, the 8500 interpolates intermediate frames. Going from 24 to 120 frames means that we have to increase the frame rate by a factor of 5. In that example, we do motion estimation between those frames A and B and calculate 4 interpolated frames, which will be output at intervals of 120 Hz. As a result, you get much smoother, natural-looking contents at full HD resolution. The last feature I want to point out allows us to not only improve picture quality, but at the same time reduce the power consumption. In an LCD TV, by far the most power is consumed by the LCD backlight, and that in a very inefficient way. Because most of LCD TVs simply have their backlight completely on for as long as the set is powered on, and this of course has 2 disadvantages. First, it always consumes full power, even for dark scenes, which would require much less light. Secondly, the LCD screen can't really block the backlight completely, so often very dark sequences, in very dark sequences, there is still light passing through the LCD. Thus, the black level of LCD TVs is usually much worse than CRTs or plasma TVs. 2D local dimming provides a solution. The TV doesn't have a single light source anymore, but a matrix of LED backlight segments. In the 85500, we analyze brightness of the video signal and then create a backlight output map here, assigning a light level per backlight segment and then communicate that output map to the panel. At the end, we need to adjust the video input through a gain for the chosen light level and the interference with the neighboring segments. And the result is amazing. You get an average power saving of about 50% for the backlight and significantly increase contrast and black level. So let me come to my conclusions. The PNX 85500 is the world's first DTV SoC in 45 nanometer, integrating TV front end with 120 Hz frame rate conversion, allowing TV manufacturers to develop a global chassis around it at very low cost. The main challenge moving from 90 to 45 nanometer technology was definitely the increased complexity of such a large and heterogeneous design. Designing a system that meets bandwidth and memory latency requirements had to be done in several iterations of performance analysis and architecture optimization and tuning. Running complete use cases on a SoC emulator with the actual TV software was a very crucial step for the bring-up. The result was very impressive. When the first silicon arrived, it only took a couple of days to have the first use cases duplicated from the emulator on the silicon. And after 2 weeks, we went to customers to demonstrate the full TV application running on a TV 550 platform, a reference platform. So what is next? On the one hand, the drive for higher integration continues, like ATSC channel decoder is one of the next steps to get in. Further improvement of the picture quality always is important, but on top we will support new features, especially those which will soon end up into mainstream TVs. Possible candidates for that are yet another increase in frame rate to 240 Hz, support of 3D television, and higher than 1080p resolutions, like Quad HD. So all those features will certainly make the other chips you consume on the front end even more tasty and crunchy. With that, I want to conclude my presentation. Thank you, and I'm open for questions.
So we have time for a couple of questions. I'll start off since I don't see anyone yet. So Ralph, if I'm a content producer and I work really hard to get just exactly the images that I want, and then I show them on your TV, you're telling me that you're going to screw up the sky color and change the skin tones and change the backlighting. Is that right?
we improve the picture quality significantly by doing this. And of course, picture quality is very subjective. That's why you have all these controls to set it to your personal favor. And different people like different settings there.
Over here.
For a great talk. I'm Thomas Pileski from Micron, and I was just curious, I know nothing about the fine-grained backlight control. How many regions do you split up your backlight into, and are they stripes or checkerboards? What does that look like?
Usually they are, well, it is basically a variable number. The more segments you have, the higher your potential energy and savings and picture improvements, but the more processing you also need. So for these backlight lit TVs that have just backlights on the top and on the side, you usually have in the range of 10 to 20 regions. If you have real LED backlight, most of the TVs currently use about 100 regions. And well, if you go to 200 or so, that's still an interesting increase. The mic is not on?
No, it's not. Now it is.
Yeah.
Deepak Sherlekar, Viraj Logic. You said that the DDR interface had only about a 70% efficiency. Is that something which is a result of the application or an inherent limitation of the controller?
Well, to some extent, it's inherent in DDR, in DDR spec, that you don't get 100% efficiency out of it.
No, I was more interested in why it is
70
not 90% instead of 70%.
Okay, so it depends on the transfer size and transactions that are done on the DDR. And we have a wild mix of different IPs in there. The highest, we approximate that we get 81% for most of the video IPs that have long bursts of 256 bytes. But then there are also very small ones that have very short transfers that are much more inefficient. So the average that we calculate is 71.
Okay, thanks.
Yeah, Chuck Thacker of Microsoft. This thing clearly has a lot of software, and I noticed that it has also an Ethernet interface. Are you going to have a Patch Tuesday for this device?
A what, sorry?
Patch Tuesday?
A patch? Well, I mean, already with the TVs that you can buy these days without Ethernet interface, you go to the manufacturer and can download an updated firmware image on a USB stick. So with that kind of connected TV, you don't need to do that anymore. I'm very sure that there will be firmware updates coming out on a regular basis for TVs.
Thanks, Ralph.
Okay.
So our next speaker is Shorin Kyo from NEC. Shorin received his PhD in precision engineering from the University of Tokyo in 2004. He joined NEC in 1989 and is currently a principal investigator of system IP core research laboratories at NEC. Shorin?
Okay, thank you for your introduction. I'm Shorin Kyo from NEC Corporation. And today my talk will be about the IMAP CAR2, which is based on a new idea to switch dynamically from the SIMD mode to a MIMD mode, and in a very low cost. So, and my talk today will cover these contents. First, I will describe the design trends and the issues in our target fields, and then our approaches against these issues. And then I will describe the IMAP CAR2 processor core design features. And finally, some application mapping schemes and also the benchmark results. And here, this slide tells about the requirements of in-vehicle vision processors, which is required to achieve this kind of applications, such as traffic sign recognitions, pedestrian recognitions, to prevent accidents and provide more safety drivings. And in order to achieve this, these various kinds of applications, the requirements against the in-vehicle vision processors can be summarized as a high performance, high flexibility, and power efficiency, because you have to process the streams of video data in real time, and there's a lot of applications you have to do. And again, you have to put in a very low price and easy cooling, because the car may drive at under the equator or at the north or south poles, and you cannot ensure that you can always cool down the chip. So actually, they don't want to have a power consumption more than 3 watts. And so here are some existing approaches today. And now we have, most of them are using DSPs with some SIMD extensions. However, they are lacking of performance. And so several straightforward ways to overcome these issues is to enhance the SIMD part, make more wider vector length of SIMD. But it's cheap, but actually it has only limited applicability. And you can also increase the number of cores inside. Okay, this is more general purpose, but actually it's more expensive than using the SIMD. Okay, so 2 of them each has pros and cons. So a wonderful idea maybe is to have a heterogeneous approach, having both features, SIMD plus MIMD. Okay, that's a good idea. However, that is in fact a kind of trend nowadays. You can see that for example, the multi-core CPU plus GPUs have high to medium, high SIMD accelerators being added. And you can see, for example, the cell processors has SIMD equals to MIMD combinations. And you can see there's also some multi to many cores which have SIMD instructions in them. Oh, these are also a kind of the design trend nowadays. However, we have to think more precisely. Suppose we have a die which we can fit n numbers of MIMD cores. And so, this the x-axis shows that the amount of SIMDizable portion in the applications, and otherwise they are MIMDizable. And here, the y-axis shows the maximum speed up. And if we have n cores, n MIMD cores, actually the maximum speed up is n. And we can also integrate instead of n MIMD cores by integrate n times m SIMD cores. In case of the one MIMD core equals to m SIMD cores. Because everybody knows that a MIMD core is more expensive in die space than a SIMD core. So now it can fit n times m SIMD cores. And the performance expectations will be something like this. So what is the SIMD plus MIMD means? It means that, okay, so the same die space can also fit half by half combinations. And the performance will be just like this. And what does this mean? It means that the performance is just average. You cannot get better performance in the against a performance against an application which have more SIMD. And this is the cons of the SIMD plus MIMD. The cons of SIMD plus MIMD appears here and here. And of course, they are better in here, but it's just some kind of performance is simply average. It's not a magic. And so our approach is not SIMD plus MIMD, but we want to dynamically switch from SIMD to MIMD or back. And okay, so we start from a highly parallel SIMD configurations, which is here. And we want to perform mode switching to take all the best. And of course, the issue we have to solve is to how to do that in a very low cost. Okay, that's our issues. And I will talk about how we do that. So first of all, I want to introduce our previous design, which is called IMAP architecture. We have published a paper in the ISCAR 2005. about that, and it's a configuration of a memory array, each equipped with a VRW data path. And we have integrated 128 of them, and which we call it, we have made it a product called IMAP car. And the IMAP car-based products can be found, for example, currently in the Toyota Lexus, which functions as stereo vision engines for the Toyota Lexus pre-crash safety systems, which helps you to brake if you are going to struck the obstacles. And the next generation IMAP car 2 design focus on to further adapt its architecture to the nature of the real image recognition applications, which is the SIMD plus MIMD, which you can found illustrated in this here. And actually, for image processing, we have 2D data, and we want to extract the feature data, first of all, from the pixels. And where we have a very large uniform data pair natures inside, so which is actually very suitable to be done in the SIMD way. And next, we have to work against each regions which is extract to be candidates. We have to verify them again in order to get a final decisions. And in such phase, we actually have to do some non-uniform region of interest processing, which is actually suitable to be done, more suitable to be done in a MIMD way. And actually, in our previous design, the IMAP car, we do the SIMD part very efficiently, and then we have to do the region of interest processing one by one. And the target design goal of our IMAP car 2 is, first of all, we want to speed up our SIMD performance, of course, and further, we want to also speed up these portions to make it to be done in parallel. And okay, so this slide shows what we have done for the SIMD enhancement. And we have increased the number of processing bits per cycles twice. And also, the bandwidth of the memory access per P is doubled, and which is shown here. And also, the control processor is increased from the number of instructions to be issued is increased from the 1 to 6 per cycle, and FPU is added for in the control processors. And then we also have to enhance our P interconnections, where in the previous design we have only neighborhood connections, but in this design we have two-stage structures of the ring connections, which allows the P's to exchange data in any P ways, so that the flexibility is raised in the SIMD mode. And all these things are covered by the power and area are maintained by the process shrink. So we don't get more power or more area for these enhancements. And for the MIMD support, we tried to support the MIMD mode in a very low cost by trading off performance and flexibility. That means that we reuse the hardware resource of 4 SIMD PEs to form one MIMD PUs. The PU means the processing unit in the MIMD mode. And again, also we enabled the 3 PUs data bus to be reconfigured as a floating-point unit. I will go into some more detail about this. And okay, here is the major hardware resources of 4 PEs. And we have reused 2 PEs scratch pad RAMs to be the instruction cache body. And we have added this iCache controller and instruction fetch units. And 1 PE's registers are reused as the iCache data tags. And for the data cache, also we use the two PEs ROMs, and we add the data cache controllers. And finally, we have reused the PEs, the data passes, 3 PEs data passes to form the floating-point units, and the 1 PEs the registers to behave as the floating-point pipeline registers. And this shows that how it shows an example of how we reconfigure the PE hardware resources to form the instruction cache. And we have fully reused this part, which is the scratch pad RAM of 2 PEs and the data registers of 1 PEs. And the major added circuits are here, written in the red arrows and the multiplexers. So the major overhead is the several 2-to-1 multiplexers plus small I-cache control logics. And this is a breakdown of the gate count distribution of one 8PE tile, where, as a summary, the MIMD overhead, supporting overheads in the hardware, in the circuit area is that just occupies 9.7%. And which means that, okay, we have the control versus the compute area breakdown here, and we add a 9.5, 9.7, 10%, near 10% overhead, then we got the MIMD support. And it's notable that we reuse the circuits so that even though the MIMD needs a lot of control circuit, we don't have to add them. We just reuse the hardware resources of the SIMD mode. Okay, I will talk about application mapping. So to program in SIMD mode, we use ANSI C+ straightforward vector data type enhanced language called 1DC. And this language works on the memory spaces called global scalar and private 2D. It's local memory. And if the user writes the normal C syntax, then the data are allocated on the scalar memory. And if they use a SEP keyword, then these variables are allocated on the private memories, each of which contains a number of PE elements. And if you add an outside keyword, then that one is not here but here. And the programmer has to do, what the programmer has to do is to explicitly transfer data from outside to inside using such kind of system functions and do some operations as they want. They can use also scalar data, and they can use the SEP data to indirect access the memories. And then finally, they have to write it back to the external memory if they want. And the write back is we call it line transfer, because the data transfer is done in the bus way. It transfers the number of PE bytes per, which we call it a line. And the user can concentrate on designing their own kernel, because we also provide callback function, which users just have to use their functions pointers as the parameters of that function. Then the data transfer can be managed by the callback function. And in designing the user's own SIMDized kernels, we have thus far noticed several parallelizing methods, which is useful for image processing. And you can see that all the PEs can, because all the PEs can access to a different address of the memories, the PEs can traverse across the 2D spaces as they want, according to the required restrictions in the application. And okay, so they can design their own algorithms in a very efficient way based on these envisioned parallelizing techniques. And in programming the MIMD mode, we provide hardware support of the master worker style of task allocation. There's a C-ring which delivers the messages between the PUs and between PUs and between CP and PUs, where the CP is behave as a master and all the PUs can behave as a worker to receive one-to-one or one-to-many or interaction task messages. And also the M-ring is used to transfer ROI data, region of interest data, and as well as serve as the path for any cache miss or cache fill request. And I want to introduce more about the ROI data transfers, which if we don't have that, then we have to actually, when we want to process ROI data, we always need to transfer some unused data. But by using the ROI and ROI read and ROI write, we can actually transfer the data we really want, thus reduce the memory traffic. And we also support some data broadcast from the CP to the PU at the startup, and also some cache bypass access for applications with little data locality. And here, this slide provides the summary of the programming support. In SIMD mode, we use ANSI-C with long vector data extensions. And the memory access is very flexible. And in the MIMD mode, ANSI-C is used, and floating point operations is available, and the user performs thread programming. And we have also prepared lots of libraries which can let the users to concentrate on their own original algorithms development. Okay, I'll show some benchmark results. This benchmark results is got by using a 1DC compiler, compiles the 1DC code versus the C compiler, which we use the GCC with these options. And okay, so the first group is that we used 120 PEs operating in 108 megahertz. And the performance is up to 9 times versus a general purpose processor works in the 3.3 gigahertz. And okay, so this can be some representation kernels for some tasks which have lots of SIMD natures. And this class is several algorithms which include sequential parts and SIMD parts. So, and because our architecture is a very tightly coupled SIMD array to the control processors, they can exchange data in one cycle. That's why such kind of sequential plus SIMD is also good for our architectures, and we achieve the similar performance as the 3.3 gigahertz, which is 30 times faster operation frequency than ours. And the final one is the N-Queen, which we use. We switch our the operation mode from SIMD to MIMD, so we have 32 PUs, which operates in 108 megahertz versus the 3.3 gigahertz, and we got a comparable performance. And for this case, actually the PU scales well according to the number of PUs being used. And here, this is the comparisons of the SIMD switching to MIMD performance versus its previous design. And okay, first, here, these are two applications which need first SIMD operation in the first phase, and then MIMD operations against some region of interest. And we got first 5 times speed up by using the SIMD mode comparing with our previous design. And further, 2 times speed up in maximum for these cases by switching to the MIMD. And here is the speed up curves. And we are happy because we only need the 10% overhead to get up to 12 times speed up for the MIMD portions. And okay, so the pedestrian detection is really typical examples, which the 2 times performance speed up is achieved by process technology changes. And then we get another 2 times performance by SIMD, MIMD mode switching. That's what we are expecting, and that this is a typical result of it, to showing that. And here we have developed a prototype which integrating 120 PEs, which can be switched to a 64 PEs plus 16 PUs or 32 PUs. And here are some figures, the performance in each mode. And okay, this is the evaluation board, and it's now fully functioning, and which we use to get the benchmark data. Okay, and this is what we are going to provide to our customers. We are manufacturing 32 PE versions, 64 PE versions, and 120 PE versions, so that our customers can use the same architecture across their several from cheap cars to expensive cars. They can reuse their codes, and so thus reduce their software development times for each model. Okay, here is the summary. We have proposed a tileable SIMD MIMD core, which in this talk which has a potential superior to SIMD plus MIMD, and that feature is obtained by only a 10% hardware overhead compared with plus to a purely highly parallel SIMD. And that such kind of low cost is achieved by trading off parallelism, the number of PEs with the flexibility of using different program counters to work. And that features fully adapt to the SIMD, MIMD nature of our target application. And we also envision SIMDizing and MIMDizing methods, which can reduce our customers' design efforts. And finally, we provide platform approaches, which will facilitate the performance scalability and code reuse. Thank you very much for your attention.
So Shorin, this seems like a very unusual reconfigurable processor, and you certainly talked about the overhead, the hardware overhead, but you also talked about applications that seem to require some dynamic reconfiguration.
Yes.
Can you give us an idea of what the software overhead is for making those reconfiguration steps?
Okay, so the switch from between modes takes only 3 machine cycles. However, when you switch from SIMD to MIMD, actually you have to, you got a cache miss at the beginning. So it's, you have the instruction cache miss and data cache miss. However, we provide a hardware support of the broadcast from the CPU to all the PUs or certain PUs at the same time. Some functions, user already knows that it is required for each PU, or the data which is required for each PU, so that you can, before activate or switch to the MIMD mode, you can broadcast all those data beforehand, so that you can reduce your startup overhead. And in that case, the switch occurs only for 3 machine cycles. Okay.
Are there some other questions from the audience? If not, Shorin, thank you very much. So our next speaker is Hideaki Kido from Hitachi Research Labs. Hideaki is a researcher at the Hitachi Research Labs. He graduated from Kyushu University and joined Hitachi in 2007. His interests are in both hardware and the software of image processing systems. He's currently studying image processing accelerators and pattern recognition algorithms, mainly for automotive safety systems. Hideaki?
Thank you very much. Sorry. Today, I'm going to talk about SoC for car navigation systems with a 53.3 GOPS image recognition engine. Excuse me. Our contents are following. First, car navigation requirement and new SoC. Second, our new image recognition engine called IMPX on this SoC. Third, we introduce practical application with IMPX. Last, we summarize this presentation. Let me introduce the background. In the near future, we think these advanced car navigation systems will be required. I explain it in next three categories. Excuse me. Navigation, amusement, and safety. Navigation will supply more driver user-friendly interface and richer graphics to provide traffic information. And amusement will supply digital TV display or audio playbacks to entertainers. And safety, it is very important for the advanced car navigation system, will help us to avoid the traffic accident by object recognition or passive and active safeties. So we think these advanced car navigation systems will supply much applications, assisting and entertaining our driving. Today, we propose our integrated one-chip solution, realizing these systems. To achieve the advanced car navigation system, there are many demanded technology. For example, navigation will require high performance and various graphic processing technology, and of course, GPS technology. Amusement needs multimedia interface technology and audio or video processing technologies. And safety will require high-performance embedded image recognition technology and connection with vehicle control technology. Today, we mainly focus on this image recognition technology. This technology is for understanding our vehicle's circumstances with onboard cameras. Additionally, all these categories need fundamental technologies like high-performance processor, high-speed bus and data I/O technology, and multi-application supporting technology. Our solution have these technologies into one chip. Actually, we have released several one-chip solutions for embedded car navigation systems. Lunsas has #1 market share worldwide in microcomputer or car navigation systems. For high-end model, this figure shows the product lineup, and the left edge of rectangle shows its release date. And in 2004, we first released SH-Nav1, and in 2006, we released SH-Nav2V, that is world first SoC embedded image recognition engine. These two models succeeded because we integrated many customer needs and took future needs in advance. And this year, 2009, we released our new SoC named SH-Nav3. SH-Nav3 is next generation one-chip solution. It has dual RISC processors, SH4A, and several modules like 2D, 3D graphic accelerator, image recognition processing engine, and video input-output, GPS supporting module, and audio encoding or decoding modules. Additionally, there are many external peripheral interfaces like PCI Express, USB 2.0, serial interface, and we are supporting DDR3 memory interfaces. All these modules are connected by a super highway bus that is Renesas' original high-performance bus architecture. And SH-Nav3 supports both AMP and SMP architecture for multi-core system. And we also adopt EX-Real platform for system building easily. And it consists of domain separation technology and domain interoperation technologies. This table shows specification of SH-Nav3 and our previous model SH-Nav2V. The important improvements from SH-NAVI2B are first, dual risk processors working at 1920 MIPS. Second, new image recognition engine. And the third, rich graphics IP, including PowerVR SGX by Imagination Technology Limited. And fourth, we're supporting DDR3 memory interfaces. From the next slide, we focus on this, our new image recognition engine for automotive safety system. Automotive safety system based on image recognition is expanding its market in these days. Current demands are object recognition for avoidance of traffic accident and making more understandable images. Object recognition has to detect many objects surrounding a vehicle, like adult vehicle, pedestrians, traffic signs, lanes, and etc., to avoid dangers. And make understandable images like changing viewpoint with distortion correction will reduce your burdens. For example, when you park your cars. And the important point is that these applications have to be processed in real time. But real-time application with image recognition consumes a lot of computation power. This figure shows our estimation of necessary computation power for each image recognizing application. Max CPU performance of SH-NAVI3 is 1920 MIPS, described as red line. And as you can see, and as you can imagine, the image recognizing application can disturb the other applications working, such navigation routing or audio encoding. Some of them even exceed the max CPU performance of SH-NAVI3. So to solve this problem and to reduce the CPU occupancy of image recognizing application, we embedded image recognition accelerator called IMPX. Concept of image recognition accelerator are following. IMPX accelerates frequency used and simple function fastly. This means when we analyze the process time of image recognizing application, we notice that simple functions occupy the processing time mainly. So we made specific accelerator for them and accelerate them. The other complicated function will be computed with CPU. The combination of CPU and IMPX is very important for implementing image recognizing application for our architectures. Next concept is IMPX and CPU can access same image memory region with same distance to exercise the best performance for image recognition. The right figure shows relationship between IMPX, CPU, bus, and image memory region. Next figure shows IMPX block diagram and the other modules blocks. As you can see, IMPX and the CPU can access the same memory region on DDR3. Then let me introduce the process flow of image recognition. At first, we have to obtain the image dataset from video input module, and the dataset is transferred into memory region in red arrow. Then when we use IMPX, the data is transferred into IMPX through several super high bus, and IMPX processes the image data by line with its several processing unit and line memory. The result of data is transferred into DDR3 memory region again. And after processing with CPU or IMPX, the result of data is outputted into display unit or used for vehicle control. Next is IMPX characteristics. For high-speed processing, we adopt local parallel processing and pipeline processing to accelerate various image functions. And we also adopt function-specific accelerator named IMR for distortion correction and changing viewpoint. For integration into SoC and for versatile processing, we employ the compact architecture and programmable image processing extensions, shortly PIP, pipe architecture. Pipe and pipeline is very similar, so I'm afraid that you mix up them, but they are different architectures. Please remember. First characteristic is for high-speed processing. Actually, the engineer of image recognition wants to use many image functions, so we support the acceleration of them. For example, left above functions can be computed at 0.66 milliseconds at VGA image size. Then max performance of IMPX is at 53.3 GOPS when we use normalized correlation. That is one of the temperature matching methods. I'll give you more information about that. Temperature matching calculates similarity between temperature pattern and pattern of image. Normalized correlation is one of that, and it is very popular method. And it is defined as this formula. IMPX can calculate normalized correlation between temperature pattern and 25 area of input data at the same time. It means IMPX has 25 parallel normalized correlation computing units. And we call such architecture local parallel processing. We also employ pipeline processing that can compute several calculations at the same time, and it can conceal the data transfer overhead between IMPX and image memory region. Various image functions listed previous slides can be accelerated by these two processing architectures, and these functions share their circuits, and it enables compact architectures, compact circuits. For high-speed processing, we also adopt function-specific accelerator. It can generate image pattern for distortion correction, rotation, zoom out, and in. It is controlled by a flexible triangle with vertex dataset. And it can transfer both YUV image data format and grayscale data format. And it works at 19 frames per sec with VGA image size. Next characteristic is for integration into SoC and versatile processing. The problem when we integrate IMPX into this SoC was its high bus traffic. To solve this problem, we use programmable processing at each line with microcontroller. The lower figures shows comparison of three image functions behavior between without pipe and pipe architecture. Look at the left here. Without pipe processing, three image functions all needs data transfer between IMPX and memory region every time. So it causes 1.6 gigabyte per second transfer. DDR's transfer performance, our SH-NAV3, is up to 4.27 gigabyte per second. So IMPX consumes a lot of transfer capability of SH-NAV3. On the other hand, with pipe architecture, it can store and reuse of process data within IMPX. That means the result line data of one function can be used as the input data of the other functions or next function without transferring the image data into memory region. So we can reduce bus traffic. pipe architecture consists of microcode controller and feedback loop in red characters. Microcode controller can control store and load and select which function we use by line of image data. I didn't say about bus-side processing, but this microcode controller enables bus-side processing compared with processing by image. This slide shows evaluation of bus traffic reduction with pipe architecture. For evaluation, we choose highest corner detector that finds corner point of image object. As you can see, these these pictures in red points. It requires 14 functions, and right graph shows its process time and total bus utilization without pipe processing in green and pipe processing in blue. When we use only image processing, that means we don't use any modules except for IMPX. Pipe processing is slightly slower than without pipe processing because of line memory controller overhead. On the other hand, total bus utilization is much lesser than that of without pipe processing. Additionally, with many processing, that means we use many modules like many video input and many video output, and so on. And it causes high bus traffics. Without pipe processing, the process time of without pipe processing reaches over 31 milliseconds. But with pipe processing don't change so much from only image processing, despite of its high total bus utilization. It means pipe processing can supply the more stable image processing. Last of the presentation, let me introduce a practical application. We choose pedestrian detection with neural network to show you the performance of IMPX. Pedestrian detection is one of the important applications for safety system. And we use 3-layered neural network for recognizing pedestrian pattern. In this application, we have to process 1,600 recognition repeats. Then with CPU, the total neural network process time reaches over 200 milliseconds, and total application process time is over 230 milliseconds. We can call them real-time processing. So to accelerate them, we use IMPX. Actually, the neural network consists of 2 matrix product operation stages and several mathematical transformation stages. IMPX can accelerate both of them. Then, with IMPX, 1,600 times of neural network process time is reduced into 8.9 milliseconds, and total application time is also reduced into 29.4 milliseconds. IMPX realizes the real-time processing. Summary. SH93 embedded high-performance dual-risk processors working at 1,920 MIPS, and 2D, 3D graphic accelerators, and image recognition engine today we focus on. Image recognition engine has high-speed processing and bus traffic reduction and line programmability. And this technology achieves a one-chip solution for next-generation car navigation systems. Thank you very much.
Well, thank you. Do we have some questions from the audience? Well, it's a great application area, and we thank you for the talk. Appreciate it. Our next speaker is Aaron Partridge from SiTime. Aaron is a Chief Science Officer at SiTime. His background is in high-performance analog circuit design. He has a PhD in microelectrical mechanical systems from Tom Kenny at Stanford. His present work focuses on maximizing the performance and impact of MIMS resonator timing sources, and we're going to hear a bit about that this afternoon. Aaron?
In addition to my engineering responsibilities, I'm also somewhat of an evangelist, and so my hope today is to get some excitement to you about what this new technology is going to bring to you. The silicon MEMS oscillators are a new technology combining MEMS and combining CMOS to provide the core oscillator signal that all of the rest of the systems are clocked off of. And I'm going to talk to you today about what the MEMS oscillators are, because I don't think most of you have been exposed to MEMS yet in this form. And in order to do that, I'll tell you a little bit about their history, where they're coming from, so you can understand a bit about where they're going, how they're going to impact high-speed systems and impact your work into the future, and then where you can get some. Hopefully, at the end of this talk, you'll have an idea for what these oscillators can do for you that you can't currently get out of a quartz oscillator, which is what we're all using up till this transition in technology. And hopefully, you'll understand what you should be asking your clock suppliers to give you. You should be going to them and saying, I want the clocks to do this, and I want the clocks to do that. Because a good clock can help you in your systems. So first, a little bit about what a quartz oscillator is, and then what a MEMS oscillator is. A quartz oscillator is usually a little ceramic package with a metal lid. If you look on a board, you can almost always find a few of them. There are both crystals and oscillators. The difference is a crystal is a passive, it's a passive resonator, and an oscillator has usually a small silicon chip in there that just is an amplifier, and it just oscillates this guy and outputs a square wave. There are fancier oscillators that can do more than just put out square waves, but about 98% of the applications are satisfied by very simple things. These are built in dedicated fabs, special fabs made just for this application, just for oscillators. The ceramic packages are specialized, and the whole quartz processing is specialized. There's a lot of these made. About 10 to 12 billion of these things are made every year worldwide. That's a lot when you consider that there's about half that many people on Earth. So people in places that are buying electronics are buying a great deal of these things. There's probably 1,000 of them, maybe 2,000 of them in this room right now. Now here's what a MEMS oscillator looks like. It's a different animal. The MEMS oscillator is a MEMS chip mounted on top of a CMOS chip mounted in a plastic package. At least that's what our MEMS oscillators look like. We talk about, in this community, we talk some about beyond more or more than more. And what we're talking about usually is stacking things vertically to get more performance. So if I stack 8 processors vertically, I get 8 times their performance. You can also think of more than more as a heterogeneous integration where you get specialized functions from specialized chips. So you can think of this as a more than more kind of application. So a MEMS chip doing one thing and a CMOS chip doing the other. Okay, a little brief introduction to the history. What's important on the history is to know that these things didn't just pop up. They're not new. From a research perspective, people have been working on these for about 40 years. In fact, it's one of the very first MEMS applications that people have been trying to do. There were a lot of problems with these earlier ones, and this first one on the top is resonator. You can imagine that as a CMOS gate where the oxide is removed. And now if the gate vibrates up and down, it modulates the electric field in what would have been a solid material gate. That modulates the current. These were envisioned by their inventor, Nathanson, as an audio filter. But they were eclipsed by just analog audio filtering on the IC, and they never had enough performance to be oscillators. A lot of work was done at Berkeley in the 90s, and then it was finished in many places, but primarily here in this case at Bosch, which is what SiTime is a spin out of. Now, in addition to the MEMS resonator being important, the packaging is probably actually more important, because normally in MEMS, people used to build things just on top of the wafer. Well, that's nice, nice picture of it, but how do you package it? How do you dice it? How do you handle it? How do you sell it? All of these issues made the packaging much, much more expensive than the MEMS part themselves and limited the application. Well, for this application, stability requires a very, very clean environment, and that requires a good package. And that was the development that sort of launched this whole technology. Okay, now here's a brief introduction to how the resonators work. You think of them as a two-dimensional bell. On a bell, you hold it in the center, on the top, and the periphery rings. Now, on ICs, we tend to do things in 2 dimensions. So take that bell, flatten it out. You still want to hold it in the center where it doesn't move, and the periphery rings. Let's see, that's what it looks like. In this case, these things are small, and you know that smaller bells ring at higher frequencies than bigger bells. This one rings at about 5 megahertz. Now, there are 8 electrodes built into the 8 central areas and around the outside, and these electrodes give you electrostatic sensing and drive that put the thing into an oscillation and also provide you the output signal. The lower picture shows a SEM cross-section, and what you see is a resonating beam between its electrodes, and the upper one is the chip. Well, look at the chip. You can't see the resonator. It's buried inside. That's the packaging. Here's how we do that. We take an SOI wafer. Now, when a MEMS person says SOI, they mean something different than an IC person. They usually mean a thick silicon layer, like 10 microns thick. We trench down to the buried oxide layer. We cover it with oxide to protect it. We remove the oxide from selected areas. And now we cover this with a thin layer of silicon in which we perforate very, very small holes just in the areas we want to remove the oxide. And then we remove the oxide with a hydrofluoric acid vapor. Hydrofluoric acid liquid is commonly used in IC processing, but as a vapor, it comes down through those holes and it removes the oxide as gaseous byproducts. Now, at this point, the resonator is free to stand. It's a bell. It's not being driven, but it's in there. But it's already protected. It's already protected under this layer of oxide with these tiny, tiny holes. Then we put it in an epitaxial reactor, and we clean it. Epitaxial reactors are the cleanest place on Earth when they're hot. There's nothing cleaner that mankind has ever built than a hot epi reactor. So these parts are cleaned and scrubbed, and then we turn on a little silicon that seals those little vents closed. Then we build the rest of the material on top, CMP it off, and we get a flat wafer. It looks just like a brand new wafer, except now it's got tens of thousands of little vacuum chambers inside. Then we put bond pads on top in the normal way, and that finishes the wafer. It looks just like an IC. Can't tell the difference. Can't tell if you're looking at it that you're not looking at a normal CMOS wafer, and it's made in a normal CMOS fab. And that's the important part, because then we get all of the benefits of all of the research and all of the development and all of the production tools. Okay, now the MEMS is important, but the system built around the MEMS is just as important. I might even say it's more important, because what's going on here is we are taking a modern architecture, we're transferring complexity out of that resonator, and we're putting it into the IC. And so, for instance, if I buy a quartz crystal, I get the frequency that the quartz crystal resonates at. But what if I want a different frequency? Well, I have to cut that quartz different to a different thickness and polish it to a different thickness. But there's about 200 different frequencies that people want. And what if they want a non-standard frequency? Well, you got to go all the way back to the very beginning of the process. But let's instead take a look at a modern technology. Well, we have PLLs. We've developed them over the last few years. Let's just use some PLLs. So now the customer can get any frequency they want just by programming a PLL to the right place. Well, what other things? What if I don't really want to actually calibrate my MEMS to the exact right frequency? I'll just measure its frequency, and I'll download a coefficient that multiplies it by whatever it takes to get it to the right frequency. Well, what about temperature? Frequency of the resonator changes a little over temperature. That's OK. Measure the temperature. Adjust the PLL. Well, what if I want to do something fancy, like spread spectrum? Well, no problem. See, I've got this box here that says frequency control. That's a state machine. And I can put in spread spectrum. So I can modulate the frequency at 32 kilohertz, let's say. I want a little spread. That's OK. I program to do a little. I want a lot of spread. Program to do a lot. What if I want a voltage control input? That's OK. I've got this block named I/O. That could be digital I/O. Well, we actually have an A to D converter in there, so I can measure the output pin voltage, and I can pull the frequency. How much? You want to pull at 10 ppm? You want to pull at 500 ppm? Doesn't matter. The state machine can just be programmed to pull whatever the user wants. So this is a case where if I pay for the first 100 transistors, the next 100,000 are free. And that's kind of common thinking to you, but it doesn't always extend to everybody in the industry. And in terms of clocks, it hasn't been the paradigm that people have used. But we're using that paradigm. We're taking those other 100,000 free transistors, and we're doing good stuff with them. OK, PLLs sometimes scare people. And I run into this engineer say, oh, PLLs kind of bother me. You know, they're hard to design. They could cause problems, require specialized tools. I had a mask set that crashed once because of a PLL. These are all true. It takes specialized tools. It takes people with specialized backgrounds. And they are analog. And in a digital environment, they're getting harder and harder to build well. And as we scale to smaller and smaller dimensions, they're getting harder to do well. So luckily, we're specialists in PLL. And we're going to take that PLL function off of the digital chip that you're building, and we're going to put it onto an analog environment. For instance, we have very quiet power supplies. Your digital chips are very, very noisy. So you want to get those PLLs off of your chips. We use some of the most advanced PLL technology in the world. We use LC, FRAC, and Sigma Delta PLLs. These are not something that you would normally want to put into a high-end digital chip at all. But they give us the power to do all of this frequency manipulation with very low noise, very low power, and a great deal of control. So now we've got an ASIC, and I've got a MEMS. How am I going to package them? The beauty about this packaging is it's really simple. I take a lead frame. I mount an IC on top of it. I mount the MEMS on top of the IC. I wire bond them all together. I put some plastic around them, dice them, then I test them. This is normal IC packaging, and that's the whole key. It's very important in IC packaging to stay in the normal process because it's a serial process, right? All our wafer fabrication is parallel, but ICs are serial. It's one die at a time. So if you get too far off the beaten path, it becomes very slow and very expensive. This is normal IC packaging. How well does it work? Well, most people want to know about how well the frequency is controlled over temperature. This is a standard set of production parts that we measure in every lot. We do a lot control. As you can see, most of them are 10 or 15, within 10 or 15 ppm over temperature. And we sell this into a product category that's in this case, 50 ppm. So they're plenty well controlled. What about reliability? Well, reliability is a really lucky thing that happens here. This is a list of the tests that we do to qualify the parts. You don't have to really read down the list. The thing I want you to see is the fails column. Zeros, all zeros. You're used to that as IC designers. You don't normally expect to see your chips have any kind of failure parameters. But you wouldn't be expecting that if you were a quartz manufacturer. The reason is because we spend billions and billions of dollars controlling our CMOS fabs. How much over the last 40 years? Any guesses? Maybe, I think hundreds of billions of dollars. We adopt all of that, that skill, that quality, that understanding, because our stuff is just built in standard CMOS fabs. Okay, so now let's talk about clocks in high-speed systems. This is my generic high-speed system diagram, and there's some clocks around it. There's 3 categories of clocks in this system. There's clocks that clock state machines, the CPUs, the GPUs, the peripherals. There's clocks that clock the parallel memory transfer, and there's clocks that clock the serial memory transfer. So those are the 3 categories of clocks I'm going to talk about. Let's talk about the state machine clocking first. So in this case, the clock comes in, goes right into a PLL. That usually goes from a 27 megahertz clock up to a couple of gigahertz, and then to your logic. That PLL is making all of the edges that your internal clock uses. There's 100 edges coming out of it for every edge that goes into it. So it's responsible for the clock. So we say, well, the outside clock doesn't matter at all. It's not making the edges, right? Wrong. The outside clock can do things that make life easy or hard for the PLL. What you can do to make life easy for the PLL is to move up the reference frequency. And also that little line between the clock and the PLL, that will typically go across different power supplies domains. There's a lot of noise on board that state machine. And usually you can take a very nice clean clock, and by the time it gets into the state machine, it's been trashed. So you can also run clocks in differentially. So high-speed differential helps. Here's some typical requirements for state machine clocking. They are the most lax of any of the requirements. 25 to 50 ppm typical, and frequency stability, period jitter, 4 picoseconds to 100 picoseconds. Pretty relaxed specifications. Next thing is parallel computing. Parallel computing is different than the state machine for 2 reasons. One is you don't own both sides of this. It's going across a standard. You may be making one of the chips, but you won't be making both of the chips probably. So you have to go with an industry standard. And second, because of the difficulty of getting data across a PC board, you have to worry a lot about eye diagrams, and the clocking, therefore, is given less flexibility. So you have to build a somewhat better clock. Not a great clock, but still somewhat better. Again, the specifications, now you'll see the key one is the jitter allowable is now gone down to 1.5 picoseconds. The third application is the toughest. Serial applications. Again, you don't own both sides of the serial link. You have to go to standards. The standards are tighter. The standards are a lot tougher because what happens is you don't even have a clock on both sides. In parallel, you had one clock for both sides. Here, the clock is embedded into the data stream and has to be pulled back out. That puts more constraints on what kind of clock you're allowed to have. So typical applications here, SATA, SAS, fiber channel, Ethernet, you this whole list. You know all about this list. The specifications here are tighter. Sometimes the frequency is down to 10 ppm. And the jitter budget is now a big issue because now the clock can actually consume some of the budget. It's no longer a perfect clock. So you have to ask yourselves, well, how much am I going to give my clock in terms of my total jitter budget? So let's look more closely at the serial application space. I have a clock, goes into a transmit PLL, goes down the serial line, comes out the receive PLL, and then the receive PLL drives the sampler. I can look at the transmit PLL and I can say, well, it's got some bandwidth. Anything above that bandwidth, any noise above that bandwidth in the clock is ignored by the transmit PLL. And then on the receiver PLL, it has a bandwidth. Anything below that bandwidth on the receiver PLL is tracked out. So what I care about is something in the middle. And I'll have a band in the middle, and I'll have the steepness of the edges. And different standards say what the band frequencies are and what the steepness of those skirts are. So then when I go through all of the different standards, the USB standards, PCI Express, the SATA, etc., I can look at the clocks and I can determine what my jitter budget, how much of my jitter budget is taken by my clock. Now, if you go out and buy a clock, the data sheets will never tell you these numbers. It's not part of the data sheets of almost any clock. You have to ask the clock manufacturer. And you have to ask them specifically, I'm using this kind of a clock in this kind of environment, is it good enough? If you ask SiTime, you're going to get the numbers like this. So here's some things that Quartz doesn't do for you that MEMS does do for you. High frequency. We've got a PLL. We can give you any frequency you want. Up to 800 megahertz differential. That will make the PLL much easier to design on board. Second, spread spectrum. We've got the ability to spread it. Some applications require, PCIe 3 requires spread. Our parts will do that spread for you. And also multi-outputs. We have some chips that have 3 outputs. Each one can have its own power supply, its own spread or no spread, 1.8 volts, 3.3 volts, different frequencies, differential, single-ended, completely mix and match any way you want. And of course, low defect, short lead times. Haven't mentioned that, it's really important. If you ask for a frequency, a special frequency in Quartz, it's going to be 3 months before you can get that crystal, because they have to go all the way back to the beginning and grind the crystal to the right thickness. In our case, we just program it. Our lead times are 2 weeks for any frequency, standard or specialized. Here's a few unusual things that, that MEMS parts can do. High shock. I was recently told about a test one of our customers did. Every single Quartz part failed. Our parts all passed, of course. Wide temperature operation, I've got a plot here. Frequency variation from -70 to plus 130 degrees C, plus or minus 5 ppm. There is not a Quartz part on Earth that can do that. Ultra thin packaging. This is what we call the UT package. It's only 250 microns thick. That's the whole thing. That's the ASIC and the MEMS, all ground very thin and put into there. That's the world's thinnest precision oscillator. So here's parts that are available. We have low power, high stability parts. These are down to 3.5 milliamps. We have high performance parts, differential, up to 800 megahertz. We have spread spectrum parts. We have multiple output parts. We have voltage control parts. We have automotive parts, all online now. Last slide. This is a bit of a technology transformation, and you've all seen them before. One technology replaces another. It's pretty common that Quartz replaces something else. Like we all have memory sticks that got passed out with the proceedings on them. Well, that would have been disks just 2 years ago. And so here a piece of silicon has just replaced a 20-cent piece of plastic. And it did it because it could offer more features. And it could do it more reliably, and it could do it more readily, and it could be changed more recently at the last minute. This is exactly what's happening in the MEMS timing field. We are there. We just started out. These things have become available, the very first ones about 2 years ago, and now the low power ones are just coming online this month. The differential ones have been online for about almost a year, but the multi-output ones are coming online next month. So that's just where we are. We've just begun to fill out the space. There's 10 or 12 billion of these things sold every year, and it's going to take a while for the whole industry to transfer over, but it will. The features are there, the reliability is there, and the cost is better on a silicon part, and as we learn more about what people need clocks to do, it'll be embedded into those other 100,000 free transistors. So that's basically the thing I want you to understand.
Thanks, Aaron. Do we have any questions from the audience? Oh, Bob. Go ahead, Bob.
Bob Stewart, Stewart Research. I have on my left wrist a wristwatch which has a free-running quartz crystal. It'll keep within 1 minute per week of WWV. I'm curious if I count down your MEMS oscillator, how stable would my wristwatch be? And have you done it?
Yeah, so the answer is your wristwatch is pretty stable because it's at a pretty constant temperature. You're not going to have a wristwatch at minus 30 C or plus 100 C. It's always going to be your body temperature plus or minus 5 degrees. And in fact, the wristwatch manufacturers know how much of the time your wristwatch sits on your bedside table and how much is on your wrist. And they know the average temperature of your bedside table, and they calibrate that wristwatch so that on average, it's following WWV. But during the day, if you actually watched it, it would run a little bit ahead during the day and a little slow at night. The reason is because your wristwatch is actually only accurate over temperature to about 200 ppm. So,
have you made one? A wristwatch?
I've made demo systems with that output wristwatch kind of frequencies and showed seconds. But there's a large application space in that. There's a few billion of these 32 kilohertz crystals sold a year, and it's definitely within the technology space.
One more?
Todd Besnick, ex-electrical engineer. So I got intrigued by your answer. So I have one too. My Rolex is at the watchmakers, so I have this quartz watch. And I grew up in North Dakota, and when you walk to school, to your calculus class, when it's 25 below zero, your LCD would be frozen when you got to class. And my watch was always pretty accurate too. So when I take this and I put it in my freezer for a week when I get home tonight, how much time is it going to lose?
The clock in your freezer, the crystal in your freezer will run about 20 or 30 ppm slow. It's parabolic with temperature. So there's about 88,000 seconds in a day, so that's about 12 ppm. So you're going to lose about 2 seconds a day in your freezer.
Thank you.
Okay, thank you, Aaron. We have a break.